Okay, I'd like to give one more algebraic style lower bound, which extends some of the ones we've already seen here. So this is a theorem of Füredi, also from 96, like the previous ones here. And this gives us the extremal number of k2t. Okay, so a complete bipartite graph with one class of size 2, the other of size t. If you forbid this, in other words, if for every two vertices you don't allow them to have more than t common neighbors, we have the extremal number, the max number of edges in that graph there. Okay, so let's fix t is at least 1 here. The form's going to be a little bit different. It makes the computation easier later. The extremal number of k to t plus 1 instead of t. We could write t and then set be t at least 2, but the statement that comes out from it isn't as nice and won't work. So this is asymptotic to 1/2 root t times n to the 3/2. Okay. All right, so what's the proof? So what this means is that we're going to be making a lower bound because the upper bound on this follows immediately from Köveri-Turan or Füredi's result, which gives the same in the case when this is 2. KST says 1/2 root t minus 1, but that's for t here. We have t plus 1, so t minus 1 becomes t n to the 3/2. Okay, and there's an error term, but that's absorbed by this asymptotic 2 here. Okay, so upper bound is by KST, Köveri-Turan. Okay, so the lower bound is what we're going to do. So we're going to construct a graph G with this many edges and no k2t plus 1. Okay, and as before, this graph is going to be on a vertex set that depends on a prime or a prime power, so it won't be true for all n. But we can do the trick we did when we created the C4 free graph and just add a few more isolated vertices. It doesn't affect the error term. I'm not going to work that part out though. Okay. All right. So t is fixed. Let's let q be a prime power. All right. So a prime raised to an exponent, such that t divides q minus 1. Okay. It's not apparent that such a thing exists, but it follows from a theorem of Euler. Okay, so this exists by a theorem of Euler, a fundamental number theory theorem. We're not gonna state it or certainly not prove it here. Okay, and I'm gonna construct a graph on FQ cross FQ. Well, it's actually not on that, but that's what I'm gonna start with to build up my graph here. Okay. All right, so what I'm going to do is, let me just state it here. I'm going to construct an n-vertex graph with no k to t plus 1 in it. And that graph's going to have enough edges here. It's going to be in terms of q, but then we're going to convert it to n as we go on here. Okay. All right, so let fq be q element finite field, just like we've been using before. This is the integers mod q. You can think of them. Okay, so you got everything you want with that. And now, because we have that t divides q minus 1, it means that if we think of fq minus 0 as a group, right? So just take the group elements, 1 up to q minus 1 of this. There are subgroups, and there are subgroups of order t, and there are elements of order t. You don't really have to know your group theory much here. I'm just going to tell you that let h be an element of order t, okay, and those exist because of this condition here, and not because of the Euler theorem, but I guess it is also because of the Euler theorem. So what does that mean, that have an element of order t? It just means that if you raise h to the t, you get back 1. You get the multiplicative identity back, okay? That's the first time you get it. So those exist by this, and so in other words, there exists a subgroup h, which can be written in the following form here: 1 little h squared, and so on until we get to little h to the t minus 1. Raising little h to the t will bring it back down to 1. That's what it means to have order t there. So the fact that q is a prime power and t divides q minus 1 guarantees the existence of this special subgroup. There may be others, of course, but I'm just talking about this. There's one subgroup that I'm going to use there. That's going to be the special one. It's a t-element subgroup of FQ minus 0. Okay, so now we're going to start to build up the vertex set here, but what I want to do first is we're going to be working with FQ cross FQ, and we're going to say the two elements, let's say A comma B and A prime comma B prime in FQ cross FQ minus 0, 0. I don't want to deal with that element there. These two, these are not vertices yet. So these two elements that live inside of here are going to be called equivalent, So we're defining a term here for this, this proof here. They're called equivalent if I can find one of these special elements that I multiply through by that to get that. So if there exists an h to the alpha, right? All the terms in here have form h to the something. So if there exists an h alpha such that h to the alpha times a equals a prime, and h to the alpha times b equals b prime. Okay? So if you can convert this pair of elements, each in FQ, to this pair of elements, each in FQ, by just multiplying through by this h to the alpha, then we call those two elements equivalent. Okay? And then denote all pairs equivalent to AB by the following. I'm going to use these braces AB. Okay? So AB, this is a collection of pairs here. This is a collection of pairs of this form, which it's these A prime B primes that can be formed in this fashion here. Okay? So this thing actually contains, in a sense, this collection, pairs AB, right? I can start with AB and convert them to A prime and B prime by just multiplying through by those. All those formed that way would be equivalent. So that'll be this class of equivalent pairs there, okay? So my graph is not on these pairs, but it's on the collection of pairs that are all equivalent to each other, okay? So G has vertex set of all, I'll call them classes A, B, okay? So what does this mean? The number of vertices in my graph then is what? Well, I have FQ cross FQ minus 0, so that's Q squared minus 1, but that's not the number of vertices because I squeeze I squeeze these pairs together if they're equivalent by this thing. How many equivalent pairs does this have? It has 1 for each of the elements in the subgroup here. So my number n is just this divided by t. I just absorb them up, okay? This is a different, notice this is a difference of squares, one of which is this, so t divides it, so this is actually an integer. So we can actually concretely say that that's what n is, okay? Now what I'm going to do is I'm going to prove that all the vertices in this graph have degree at least q minus 1. Okay, so how are we going to do that? So vertices, AB, remember AB is a collection of pairs that are all equivalent. So vertices AB and XY are adjacent in G if, and only if, they satisfy the following. It's not really an equation, but the following condition. If I can do the following. If I can take A times X plus B times Y, right? In other cases we've seen that this equals 1 or something. If this product and sum is of the form this. So if it lives inside of H, okay? You don't really have to grasp why or why not that might occur, but if I have a pair, AB, and remember AB represents a bunch of pairs, but I can just take any of the ABs to like be the values here, and XY, if I multiply them and add them in this fashion, if it spits out something that's one of these guys here, I join them by an edge. If it doesn't, I don't join them by an edge, okay? You'll notice, if you sit down and think about this for a little while, if this is true, right, if A, X, B, Y is in H, then it also actually will hold very easily for if I replace AB with A prime, B prime, with something else that lives inside of there, right? If I put A prime, B prime here instead, that will also live in H. Why is that? Well, A prime is just H alpha A, and B prime is just H alpha B, and if you have those H alphas here, you can pull it out front, and what you have inside is inside of H, times H to the alpha still lives inside of this here. Okay, so that's why equivalence sort of still works here in defining the number of edges. So that's how the edges are defined. Okay. Now I'd like to figure out the degree. So what is the degree of, say, AB? Okay. Here we can assume that B is non-zero, right? We have that you don't have the pair 0, 0, so at least one of them is 0. Choosing either A or B to be non-zero, either way we'll get the same count for the degree. Okay, so what am I going to do here? I'm going to fix X in FQ. Right. So here's the degree here. I want to find the number of pairs XY of this form, right, in this equivalence class, the number of pairs XY that satisfy this thing here, that force something to be an H. So I'm going to fix X to be there, and I'm going to fix H to the alpha to be in H. Right? So I have Q choices for X, and I have T choices for H to the alpha. Keep those in mind. We'll use those in a moment. Okay? So if I fix those two things here, there is a unique solution to the following equation. AX plus BY equals now H to the alpha. Okay? There's a solution to that for Y. Right? Y is the only thing that's not fixed. A and B are fixed. X is fixed. H alpha is fixed. This, let me make it so it's clearly an equality. In the field here, this equation can be solved for Y. In fact, there's a unique solution to this. Okay, so what does it mean? It means for any fixed X and fixed H to the alpha, I can find a Y that solves this equation here. So what does it mean for this guy here? It means for AB fixed, I can find, so there exists Q times T solutions to this guy here. I'm going to write it. Okay, there's that many solutions. That equation, it's not really an equation because H can take on different values, but there's Q times T, different X and Y's I can find to satisfy that. Now, that's not the degree. All right? Why is that not the degree? Well, I made this huge list of X and Y's, Q times T many X and Y pairs that kind of solve this equation. But many of them may be equivalent to this XY, right? So if I find one, there might be other equivalent solutions, right? Things of this form that satisfy this thing. There might be as many as T, okay? So I'll put that. There can be each solution XY has at most T equivalent solutions, right? So what that means is I'm asking for the degree of this. How many vertices are there? How many XY classes are there? Well, there's at least Q times T pairs that solved it, but T of those might be equivalent to each other, so there's at least Q. And we have to drop it down further by one, because one of the equivalent classes, XY here, might be AB itself, right? AXBY might be solved by AA plus BY, plus BB. That might also be an H, so I should throw that one away, okay? So one of these, this is visible, but one XY could be A, B. Okay, so throw that one away, because that's not part of a graph. So that answers the question here. What's the degree of that there? It's at least Q times T divided by T minus 1. Right? Q times T solutions XY. That's how many there are there. However, among all those solutions, each of them come in blocks of T. Okay, so I have to divide out by T of them, because these are replicate each other. And then one of those equivalence class solutions that I found could be AB itself, which doesn't count as an edge. So I have to subtract that. But what is this? This is at least, well, this is equal to Q minus 1. Okay? So the degree of any vertex is at least Q minus 1. All right? I'm going to go up here. I'm going to erase the theorem here. Let's try. Maybe I'll leave this boxed here. That's the quantity we're going. Well, actually, I'm going to show us in just a moment here that that's indeed how many edges we have, and then we only need to show that there's no K2T. Okay. So why does it have that many edges? Bear with me here. There's actually a spray. That sprays work on this, but you're not supposed to use them. It makes the board streak. So you just have to use a little muscle. Okay. I can leave the definition H there. All right. How many edges? So the number of edges in G is at least 1/2 times the number of vertices n times every vertex has degree at least q minus 1. Okay? But I know what n is. N is this guy here. So I have 1/2 q squared minus 1 over t times q minus 1. Okay? So this is approximately 1/2 q cubed over t. All right? But I also know that n is approximately q squared over t. Okay? So if you convert this, I'm not going to do the simple arithmetic, but if I want to convert this into n, you'll notice that what you get out from this is exactly this guy here. Okay? This is q cubed over t, and this is q squared over t. If you try to replace this with t, just do substitutions. You're going to get a square root t, but it's going to be on top. Okay? So this is equivalent to 1/2 root t. I'll leave you to do the computation, as I said, 3/2. Okay, so the number of edges is correct. Right? We got the number of edges we got. Now we have to finish the proof by showing that claim G is K2T plus 1 free. Okay, so we have to do a little bit more work of this fashion in order to prove it's K2T free. So what does it mean to be K2T free? Or that's talking again about the number of common neighbors. So let's look at common neighbors. So consider common neighbors of AB class and A prime B prime class. Okay, this is let's say distinct. Okay. Distinct classes. So this is a little confusing. Before I talked about A, B, and A prime, B prime were equivalent if they satisfied this. Ignore that now. This is a collection of all the things equivalent to AB. This is the class of everything equivalent to A prime, B prime. I want these to be two distinct classes. So these pairs are not equivalent to each other, okay? Maybe I should have just called them CD or something like that. But this is a pair that has it's all of its equivalencies. This is a pair that has all of its equivalencies, all t of them, but they're not the same, okay? So these two vertices, distinct vertices, I want to know the number of common neighbors of them. What does a common neighbor look like? It's just solutions. It's an xy that satisfies this for A and for B. Okay? So a common neighbor, so xy is a common neighbor if it's a solution to the following equation. So if if it's a solution to ax plus by is in H, and a prime x plus b prime y is also in H. That would make it a common neighbor, right? It satisfies both those equations at once. So I want to count up the number of ways that's possible. So what I'm going to do here is actually count up the number of solutions to this, where I've fixed the thing that it's equal to. Okay? All right, so let me erase this and just add. Let's fix h to the alpha and h to the beta, and I want to know the number of solutions of this form here. That'll give me an upper bound on the number of common neighbors here. Okay, so I fixed these two things in t squared many ways, right? There are t choices for these, and I'm asking, are there solutions x, y to these two equations simultaneously? It equals h alpha and equals h beta, and a, b, and a prime, b prime are all fixed. Okay. So if I have this form, if these equations are linearly dependent, so if linearly dependent, what does that mean? That means that this equation is a multiple of this equation. Okay? Then there exists a C such that we have the following here, such that C times AX plus BY equals A prime X plus B prime Y, and C times H to the alpha equals H to the beta. Okay, that's what it means for them to be dependent on one another. Okay, but this has the further consequence that X and Y are, you can think of them as variables. This means that CA equals A prime, and BCB equals B prime, right? That's how you get equivalence here. But it also means that C is in the big H set here, right? Look at this. This defines C here. We have h to the b equals h to the alpha times c. So h has to be of the form h to the something, right? Then you have h to the something plus alpha equals h to the b. So c is in h. But then, if c is in h, it means that c times b being b prime and c times a being a prime is exactly of this form over here, right? A and a prime and b prime are equivalent if there's some h to the alpha that multiplies through them to create those things. That's exactly c here. So what I'm saying here is so a, b, and a prime, b prime are equivalent. Equivalent. But that's a contradiction, right? Because I just started with two that weren't equivalent. They were separate from each other. Okay, so that's a contradiction. What's the consequence of that? It means that these two are not linearly dependent. It means they're independent. It means it's two equations with two unknowns, so I can find a solution. Okay, so I wanted to rule out this case. These equations have a solution. Okay, one solution instead of infinitely many, right? If they're linearly dependent, they'd have infinitely many solutions. But if they're linearly dependent, we found that a prime, b prime were equivalent, which contradicts how we started them. So let me erase this last part here. And we're almost at the end now. Okay. So these are linearly independent. So there exists a solution, a simultaneous solution, xy, to this equation. Okay? But how many of such solutions were there? Well, I fixed HA and HB. Let's put in t squared ways, right? Because I could just choose any one of h alphas and any one h betas there. So there are t squared ways of them to choose them. That produced solutions, t squared many solutions. However, what can you tell me about these solutions? They're not all separate from each other. Some of them are equivalent to one another. In fact, with a little bit of thinking, you can quickly find out that any one solution xy to this equation also produces an equivalent solution for some different h alpha and h beta. Okay, so each xy has t minus one other equivalent solutions. So the number of classes xy solving this equation is at most, or it's exactly, but it's at most t squared over t, right? Because there's t squared ways to solve it by picking h alpha, h beta, and that produces an xy. But t of these solutions xy are equivalent to each other according to this. There's one for each of these other h's there. You can convert these to new equations. So this equals t. So what does that mean? It means that two vertices, a, b, and a prime, b prime, right? Two vertices are two equivalence classes, have at most t other equivalence classes that are common neighbors to them, that are solutions to this, or more formally, solutions to this guy here, okay? That means that the maximum common degree is t. So it means that the graph is, so G is K2T free, as desired, right? We just produced an n-vertex graph that's K2T free and has how many edges? That many edges. That's precisely what we wanted to prove. Sometimes it's